At the Academy of Useless Ideas, we believe math is not only about final answers, it's about the tools and ways of thinking you gain on the way there. In this episode, we'll start a journey toward the hardest logic puzzle ever. But first, we'll make a short detour to a simpler riddle. That detour will give us a tiny language, propositional logic, that we'll reuse when the puzzles get tougher. Here's the destination we're heading toward later in the series. No spoilers today. 3 characters, 1 always truthful, 1 always lying, and 1 random. You get 3 yes-no questions. The answers come in an unknown language. Da and ja for yes and no, but you don't know which is which. And your goal is to identify who's who. We'll come back to this later with fresh tools. Before we continue, pause the video and try the big puzzle for a minute. Even if you don't solve it, the thinking that you do will make everything we build more meaningful. Also, discussing your ideas with others is half the fun. Share what you tried. In the meantime, recall that when a problem feels overwhelming, a classic strategy is to solve a smaller, related problem to learn something general you can bring back. That's our plan. The Labyrinth detour. Here's the 2 doors riddle, popularized in the movie Labyrinth. There are 2 doors, 1 safe, 1 deadly, and 2 guards. 1 guard always tells the truth, the other guard always lies. You may ask 1 yes-no question to 1 guard to find the safe door. What would you ask? You may have heard the following clever question. What would the other guard say if I asked which door is safe? No matter whom you ask, the answerer points to the wrong door, so you take the other one. It's a neat trick, but as a general method, it doesn't teach you much beyond this specific phrasing. In this series, we're interested in more than a solution. We'll change the original problem by building a mathematical model of it using a very basic formal language. With the model, we can engineer questions that work reliably, and then reuse that engineering on harder puzzles. Modeling with propositions. What's a proposition? It's a sentence that is true or false. For example, in our problem, we care about 2 sentences. The left door is safe, and the left guard tells the truth. We'll represent these propositions with the letters D and G, respectively. As it turns out, these 2 propositions are the only relevant ones to our problem, because they completely encode the 4 possible scenarios of interest. Thanks to this simplification, we're able to focus on the information that matters. Our task is to design a single yes-no question whose answer tells us whether D is true, regardless of whether G is true or false. However, before we can construct an interesting question, we need a method for generating new propositions from old ones. For this purpose, we introduce logical connectives. A tiny logic toolbox for beginners. Let's introduce the classic 5 logical connectives of propositional logic, with both their meaning and a simple example. Negation. If a proposition P is true, its negation, not P, is false, and vice versa. For example, since G says the left guard is truthful, not G says the left guard is not truthful. Conjunction. The proposition P and Q is true only when both are true. For example, D and G means the left door is safe and the left guard is truthful. Disjunction. The proposition P or Q is true when at least one is true. For example, G or D means the left guard is truthful, or the left door is safe, or both. Implication. The proposition P implies Q is false only in the case P is true and Q is false. This proposition expresses the idea of a promise of the form if P, then Q. Such a promise is broken only when P happens, but Q doesn't. Equivalence. The proposition P if and only if Q is true when P and Q have the same truth value, while false when they differ. Think P and Q are equivalent. What answers do we get to a question? We model a question as a proposition with an unknown truth value. When we ask a question to a truth teller, the answer is precisely the truth value of the proposition. On the other hand, if we ask a question to a liar, he will answer with the negation of the truth value of the proposition. To be precise, asking a question Q to the left guard will produce the following truth table. Note that this truth table is exactly the same as G if and only if Q. If we knew the truth value of G, we could deduce the value of Q accordingly. However, identifying the truth value of D directly would require a question, and we are only allowed one. Our goal is to find a question that would allow us to figure out the value of D. That is, we want a proposition Q using G and D such that, regardless of the value of G, the answer G if and only if Q has the same truth value as D. Can you figure out the desired question Q based on the following table? Although there are several techniques to find a proposition that satisfies a particular truth table, in this case we can figure out the proposition Q by comparing the truth table of Q with the truth table of the classical connectives. Such a comparison reveals that Q has the same truth table as G if and only if D. Recalling the meanings of propositions G and D, we can translate our question back to English as follows. Is it true that this door is safe if and only if you are a truth teller? Although the wording of the question seems unusual, you can verify that either guard will answer yes when the door to the left is safe, and no when it isn't. Does this help us with the hardest logic puzzle ever? The harder puzzle adds two twists. First, unknown words for yes and no, da and ja. Just as before, to attack this twist, we can consider a simpler version of the problem. Let's say now you want to figure out which door leads to safety, but in this scenario there's only one guard who always tells the truth, but answers with da or ja. What are the propositions of interest in this problem? What's the minimum number of questions that you need to figure out the correct door? How do your answers change if you do not know whether the guard is a truth teller or liar? And second, a random responder. How can you deal with the labyrinth problem if the guard is allowed to decide whether to tell the truth or lie for each question you ask? Thinking about these two twists will help you to find an answer to the hardest logic puzzle ever. For now, recall that at the Academy of Useless Ideas, the answer to a problem is not as important as the journey to discover an answer. Let us know how you do in the comments, and in the meantime, stay mathy!